Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. So we're going to be doing some math tonight. Hope y'all are having a good evening. I apparently lost my chat window. Uh-huh. Helpful. Hey, there we go. Hey, Cooler Yellow, how's it going? Sorry, didn't see you there. Goodness. Alright, well, so tonight, going to be working on, as always, just whatever anybody wants. I'm going to be doing a little bit on improper integrals, which is yet again Calc 2. I'm pretty much never going to get away from it, so it's fine. We're going to be talking about that in class tomorrow, so naturally it's something to at least attempt to work out. So anyway. And I also forgot my, like I brought the tablet home, but I forgot the glove, so my hands are all like sticky. But it's fine. Also wanted to check on stream elements and see how we're doing. Hey, there we go. Okay. Anyway. Alright, so improper integrals are those which, when you show the integral out, there are a number of different ways that this could be considered improper. One of the most basic ones is what would happen if you took an integral from like 1 to infinity of something like 1 over x dx. So in this particular case, what we see here is that we're going to take the integral just as we normally would. So we're going to look at this as the natural log of x evaluated from 1 to infinity. But the problem with this is that you can't really take an integral out to infinity. It's got to be like an infinite value. So for instance, we're going to look at this. Can't really do this. Hence the name improper. So instead what we do is we say, okay, fine. We're going to take the limit as b goes to infinity of the integral from 1 to b of 1 over x dx. This is then going to be the limit as b goes to infinity of natural log of x evaluated from 1 to b. Which is then the limit as b goes to infinity of the natural log of b minus natural log of 1. Natural log of 1 is just 0. And then here, natural log of b as b goes to infinity is going to be the natural log of infinity. So this value in and of itself is going to be infinitely large. So here, this is telling us that the integral that we had up here is going to diverge and go off to an infinitely large value. That's really our answer. All right, so we can do all sorts of fun stuff here. We can also have improper integrals that go from, say, 0 to 5 of 1 over x dx. Which again causes a similar problem. So here this is going to have to be the limit as a approaches 0 of the integral from a to 5 of 1 over x dx. So we're taking the limit as a approaches 0 of the natural log of x evaluated from a to 5. That's enough there. Which is the limit as a approaches 0 of the natural log of 5 minus the natural log of a. Okay, which is going to be equal to the natural log of 5 minus, the limit as a approaches 0 of the natural log of a. Well, here, the limit as a approaches 0 of the natural log of a starts going to negative infinity. And so natural log of 5 minus the negative infinitely large value that we're going to get here is going to get us a positively large infinite value. Okay, so we can't really, again, have it be equal to that, but yeah, that's close enough. So here we say that this is going to be from 0 to 5, 1 over x dx will also diverge. All right, so we could do several other things. What if we took the integral from, again, 1 to infinity of 1 over x squared dx? All right, in this particular case, what we get instead is, again, we have to do the improper integral thing. This is going to be the limit as a to b approaches infinity, integral from 1 to b of 1 over x squared dx, which is the limit as b approaches infinity. Here, when we take the integral, this is going to be negative 1 over x, or x to the negative first, evaluated from 1 to b. Now, this is a much more interesting solution due to the fact that here, when we do the limit as b goes to infinity of negative 1 over b minus a negative, so plus 1 over 1 when we plug these in, we can see here that the limit as b approaches infinity of negative 1 over b is 0. So we end up with 0 plus 1 or just 1. So this is a hallmark of some things that we'll probably be talking about in the future, which is that anytime you have a like the sum of the reciprocals of squares and things like that, these always end up being convergent. So they will converge to specific values. Here in this case, this particular interval converges to 1, despite the fact that it has infinite limits. The point for this one is that the x squared at the bottom, let's try that again, the 1 over x squared becomes small enough, fast enough, that it is going to converge, so become a finite value. This is also a very highly unintuitive section, because you're looking at this and saying, okay, how does an infinite number of something end up with a finite solution? This is one of the things that really held the Greeks back from being able to understand how calculus worked. And so if they had perhaps embraced that, there could have been quite a bit of difference in the history of mathematics. All right. So interestingly enough, this is also something that you could get. You could obtain this exact same result had we looked at the function 1 over x, but been interested in attempting to do a, that's not going to work, been interested in attempting to do a solid of revolution. So had we done a solid of revolution with this, right, we would end up with something that loops around the x-axis like this, off toward infinity. And it would start here at 1, 1. This particular problem is called Gabriel's horn, referring to the archangel, I think, Gabriel, who allegedly had a horn that reached down from the heavens and was able to make, allow people to hear the horn itself. Therefore, it must have been infinitely long to come from the heavens, and also here it kind of flares out at the end, just like a trumpet. And again, interestingly enough, if we draw in disks, so we do a disk method off of this, the volume of the horn ends up becoming finite because we get the result of 1 here. And if we try to find the surface area, keep in mind that the surface area is done by who's its arc length. And the arc length formula ends up being the integral, in this case from 1 to infinity, of the square root of 1 plus parentheses f prime at x squared. So f prime of x here, if f of x is 1 over x, right, this is going to be a negative 1 comes down to the front, and then this would be x to the negative second. Okay. Something's not right there. Maybe I'm doing okay, but anyway. Square root of 1 plus f prime squared would be x to the negative fourth. Am I seriously doing something wrong here? Hmm. Yeah, we're not going to talk about the surface area of Gabriel's horn, are we? Come on, man. That's what it is. All right, so the surface area All right, let's just get rid of this. Go back. That was weird. Okay. So here the surface area is going to be given by 2 pi times the integral from 1 to infinity of f of x times the square root of 1 plus f prime at x squared dx. Alright, so here the integral is going to go from 1 to infinity. F of x was 1 over x. And then we get the square root of 1 plus. Here we get negative x to the negative second squared is going to be positive x to the negative fourth dx. Okay. So on this particular one, so they do a comparison formula, which is to say that here we have this function integral 1 over x times something. And this something here, the 1 plus x to the negative fourth, all square rooted, will, for all values of x, be larger than just 1 over x. Because we have 1 plus here, again, no matter how small or large x to the negative fourth is, this will always be larger. This whole radicand is going to be greater than or equal to, well, strictly greater than 1 in here, right, from 1 to infinity. So that means that this whole integral from 1 to infinity of 1 over x square root 1 plus x to the negative fourth dx will always be greater than the integral from 1 to infinity of 1 over x dx. Alright, so our radical will always be greater than 1, so that number will always be bigger than just 1 over x. And then similarly, the integral is going to be the same. So because of that, we're going to say that already we know that this diverges. And therefore, this also must diverge. Hey Superbrain, how's it going? Yeah, sorry I missed that. It wasn't that it wasn't really a deal breaker. It was just that I completely forgot what I was doing in terms of trying to find that integral and trying to remember that this f of x is there. So that was kind of important. So anyway, yeah, if this diverges, which we already proved up here, oops, there we go. If this diverges, which we proved up here, then this also must diverge because it has to be greater than the 1 over x dx integral. So this is one of these weird things. This infinite figure of Gabriel's horn has a finite volume, so you could fill it, like literally I mean, not literally because it can't be infinitely large, but you know, you could fill this thing with paint, but then you couldn't use the paint that's in it to cover the outside. Like you could just keep filling it, use it again to paint more, fill it again, use the paint to paint more, fill it again, and it would just keep going forever. So it's just a very strange figure to try to figure out any sort of properties for, due to the fact that, again, you have these two seemingly paradoxical properties, right? That the volume is finite, but the surface area is infinite. That just seems ridiculous. But as it turns out, That is, in fact, what we see. So generally speaking, there's also going to be this whole comparison thing. The integral comparisons become a thing. So if you want to know whether a particular integral will diverge, so generally speaking, you're looking between, some a value and infinity. And you want to know if this will diverge. You've got f of x here. Or, well, okay, that's not what I called it before. I called it b. Let's be consistent. So as your b goes off to infinity, will f of x diverge? So there's a couple of ways to do that. If you can find another function, this is sort of like the squeeze theorem from Calc 1. If you can find some g of x, which will always be less than f of x for all a to b, I guess, or equal to potentially, such that g of x diverges, then f of x must also diverge. And here, because g of x will always be less than so if g of x is always less than f of x, and g of x diverges, then f of x must be more than that, so it must also go off to infinity at a slightly faster rate. Or maybe the same rate, but either way, it's going to go off to infinity, it's going to diverge. Right, so similarly, if you wanted to show that something converges, you can't do that, right? You can't say that, well, g converges, so therefore f converges, because f is going to be bigger, so that's not really going to work. However, by a similar token, you could take your f of x here, and you could find some g of x that's bigger. So find some g of x that's always greater than or equal to f of x for all a to b. Such that g of x converges, then f of x must also converge. Again, here what we're looking for is there's going to be some f that just always ends up being less than g, and if the sum, the integral of g converges, then f is always less than that, so it's going to also converge, right? And b here is going to go off to infinity. And this also applies if a goes off to some sort of value such that the function approaches infinity. That's also possible. There are some functions that climb so slowly upward that they will be finite on this end. This book gets into an example of a probability function that you end up integrating. So that's interesting. I never thought I'd see the calc-based statistics in something so early. Anyway. Yeah. Yes. So I actually had that conversation with my students last class too. Is that, you can't just say that the integral of 1 over x dx from negative infinity to infinity is 0 because this is an odd function, right? So the integral from negative a to a of f of x dx, where f is an odd function, is equal to 0. But, right, this is the thinking, but the problem is that this is an infinite integral, and so you can't do that. Specifically around 0, right? X equals 0 is the problem. So here, you'd actually have to show that the integral from negative infinity to 0 of 1 over x dx plus the integral from 0 to infinity of 1 over x dx does something reasonable. And due to the fact that both of these end up getting you natural log of x, this one's going to be a to 0, where at the limit a approaches negative infinity, plus natural log of x evaluated, nope, limit b goes to positive infinity of natural log of x evaluated from 0 to b. Right, so this this ends up, oh wait, can't do that even, because we got to do absolute value in here. Right, let's actually get the right integral. Right, due to the fact that 1 over x dx is in the negative region, that's acceptable. It's a natural log, but it has to have the absolute values around the thing. So yeah, you'd have to separate these out. Say that we want the limit, say approaches negative infinity, of the natural log of, oh, man, I did the wrong one too. Or rather, the more important one is 0. So, oh man. Limit as c approaches 0, but that's even only from the negative side. This is going to be c, and then that's going to be c here. And we need the double limit again. All right, we'll just break this because, oh well. Yeah, no, I hear you there. All right, so then this is going to be c minus the natural log absolute value of a plus limit b goes to infinity, limit c goes to 0, natural log absolute value b minus natural log absolute value c. Right. Zero from the negative, 0 from the positive. Then I'm also curious, is it even that's the problem? Because these are literally the same thing, right? So like with the absolute value in place, this is reflected. So I think you can allow yourself to say that those things are going to be the same. But, right, okay, the one you're saying. Yeah, so if you have these two, those are the problems. But again, these you can't do anything about. Yeah. It's one of those weird things. Yeah, because again, they're literally reflected, right? So that seems okay. But the A's and the B's are not. I mean, we know they are, but it's just one of those weird things. Yeah. So there's another for comparison. Another one that we can do here is taking the integral from 1 to positive infinity of 1 over x e to the x dx. So 1 over x times e to the x is always going to be less than or equal to 1 over e to the x, right? Or just e to the negative x. So if 1 to infinity of e to the negative x of dx converges, then 1 over x e to the x integrated from 1 to infinity will also. So we take the integral from 1 to infinity, or rather 1 to b, where the limit as b goes to positive infinity of e to the negative x dx is going to be equal to limit as b goes to infinity of, here integrate, it's going to be negative e to the negative x evaluated from 1 to b. So the limit as b goes to infinity of negative e to the negative b plus e to the negative 1. Right, so this will converge to 0, and this is just plus e to the negative 1. So this converges, and 1 over x e to the negative x is always less than or equal to 1 over e to the x. So therefore, integral from 1 to infinity of e, nope, 1 over x e to the x dx converges. Right, we found something that converges, and it's always larger due to the fact that x is in the denominator, so it's going to cut everything from 1 to infinity by some constant, well, by some amount. So the x value that continues out from 1 out to infinity. And at 1, they are equal to each other. So doesn't particularly matter. All right, so that's for all x belonging to the interval from 1 to infinity. Yeah. Or perhaps we did not choose the perhaps we did not choose C because it was kind of forced. But either way. Integral from 1 to infinity of 1 over x to the p dx diverges for all p less than 1 and converges for all p greater than 1. Right, we already proved that it diverges for less than or, well, for equal to 1. But if we want to do the other two possible cases, right, so we'd say I guess a good question there is, can we actually prove that it converges for all p greater than 1, given that we don't have well, that's an interesting conundrum. Oops. So that one's at least easy. So we can say that 1 over x will be less than or equal to 1 over x to the p for all x in that interval from 1 to infinity. How we do on that one? Yeah, we're good. All right, I'll bite. Wolfram. 1 over parentheses x times e to the x. Yeah, that. Oh, yeah. Exponential integrals. That's not too bad. I mean, it's only 0.219384. More digits. Yeah, I mean, not that I understand what any of that means, but... Exponential integral, special function on the complex plane. So yeah, I would have probably seen this before in complex analysis. So this is a Masters 2 type class. But I can't say I remember practically any of this. So So actually, let's just look at that real quick. So this says that if you take it into the complex plane, do some stuff with the integrals, and then bring it back, then it ends up becoming integral of x to the negative first. Well, let's just do x to the n e to the cx dx is equal to 1 over c x to the n e to the cx minus n over c integral of x to the n minus 1 e to the cx dx. So if we look at what we had, n is -1, c is -1. So integral of x to the -1 e to the negative x dx would be equal to 1 over -1 x to the -1 e to the negative x minus just -1 over -1, right? Times the integral of x to the, this is, oh, negative, oh dear. -1 minus 1 is -2 e to the negative x dx. So that makes it worse, huh? It's equal to -1 -1 over x e to the x minus integral of 1 over x squared e to the x dx. Yeah, so I think that just makes it uglier. And then we'd have to, or rather, it does something special. So that's also interesting, is that there's a summation version of this, but the index goes from 0 to n, and n is negative. So that seems like a problem. Yeah, it also says that n, that can't be right. This has to this has to fail somehow. Yeah, there are no stipulations on it. That's weird. Ow. You know what? I got it now. Okay. This one doesn't work because n is negative. Okay. So I found a different one on Wikipedia. This is e to the cx over x dx. It's going to be equal to the natural log of the absolute value of x plus summation. I goes from 1 to infinity of cx raised to the nth power over n times n factorial. That's another problem. Man. This problem's probably just going to take me all night. It's fine. N is less than 0. N factorial, where n is less than 0. Okay. N factorial is equal to negative 1 to the negative n minus 1 all over. This is negative n minus 1 factorial when n is less than 0. So let's look at this. This is going to be natural log of x, absolute value of x, plus summation. I goes from 1 to infinity of, this was going to be negative x to the negative 1 over negative 1 times this thing, negative 1 parentheses factorial is going to be equal to negative 1 raised to the negative parentheses negative 1 minus 1. Is that a 0? Yep, so that's a positive 1 minus 1 is 0. So it's going to be 1 up top. Down bottom we have a negative 1. It's going to be 0 factorial. So that's also going to be 1. So that equals to 1. I can deal with that. Doesn't mean it's a good idea. Oh no. No, 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 no. That was not the same n. That's why. Jeez. I'm fine. I'm fine. This was not the negative n that we had before. Alright. Apologies. Alright. That's good enough. Alright, then the x value that we wanted to calculate for that, right? There is some zeta function stuff. Yeah, so when I did complex, there was a bunch of stuff that we never went to. It was just like, here's a table in the back of the book. Go look it up if you need it. And we didn't really ever need it, so just, okay, it's there. As x goes from 1 to infinity, but then the natural log also diverges. But the whole thing converges. Oh man. What the hell are they doing? Alright. Yeah. Alrighty. Well, that's fun. So one of the other things we could do is look at Taylor polynomials. So that didn't work out for us, but so if we let some function be equal to summation is I. Why do they use n? I goes from 0 to infinity for f ith derivative at some value a divided by I factorial. I guess that might be why they use n times x minus a raised to the ith power. So about some value a here. And if we're going to include this, yeah, we're probably going to include it starting at 1. As ugly as that is, that's fine. So let's see. So instead of doing this as 2, hang on. It's going to be easier to... It's going to be easier to get them separately and then bring them together. I don't think I've actually ever done 1 over x as Taylor series, so this could be interesting. So I goes from 1 over x is equal to. So di dxi of 1 over x evaluated at x equals 1 divided by I factorial multiplied by x minus 1 raised to the ith power. Okay. Somebody around here is going, no! Yeah, that's the other thing is all you really need to know is that it converges. Never mind what it converges to, that's fine. Yeah, I forget exactly what I'm doing Taylor series with this group, but it's going to be certainly a few weeks at least. So 0th term is going to be the 0th derivative, so it's just 1 over x evaluated at 1 is 1 over 0 factorial times x minus 1 to the 0th power. So just 1 plus. Take a derivative of this, and we're going to get -1. So this is an interesting one. 1 over x evaluated at x equals 1, or the ith derivative of 1 over x evaluated at 1 is going to be always... Nope, never mind. Nope, I'm going to shut up now. No. I was like, oh, look, it's going to flip signs, but yeah, that's not the only thing that happens. All right, so bring down the -1, it becomes -2. Square it, it's still going to be 1. So this is going to be a -1 over 1 factorial times x minus 1 parentheses to the first plus the -2 comes down, making this a +2 over 2 factorial times x minus 1 to the second plus -3 comes down, makes this -6 over 3 factorial times x minus 1 to the third plus, are we just getting an all? Yeah. So -4 comes down and makes it 24. Yeah, okay, that's literally the same term. So, oh, it's just the harmonic series. Okay, cool. It's an alternate. Oh no. Oh no. What have I done? That's awful. No, it's turns out it's not useful. Because it's literally just going to be... Wait. Okay. No, I get it now. Oh, man. Again, Taylor polynomial. These are not actually summed up, so you can't... Okay, never mind. I'm good. So 1 over x is going to be equal to... This is just going to be 1 minus x plus x squared. Here we go. Minus x to the third plus x to the fourth minus x to the fifth plus x to the sixth minus ... Well, just literally goes on forever. Okay. So these terms aren't getting any smaller, which seems like this can only actually work between 0 and 1, and we want values greater than 1. Yeah. Yep. Oh well. Worth a shot. So that doesn't work. But that does mean that this whole thing could probably become... Yeah. This whole thing could probably converge then, but the derivatives are going to be nasty. So x e to the x raised to the negative first is f of x. And we could say that this is 0th derivative. So then the first derivative is going to be kind of interesting, I'm sure. So bring down negative x e to the x to the negative second. Multiply by, derivative is 1 e to the x plus x e to the x. All right. So negative x to the negative second. This is going to get rid of one of those. So now it's e to the negative first, negative x times 1 plus x. Okay. I'm going to regret this, aren't I? Alright, so negative e to the negative x times 1 over x squared plus 1 over x. Second derivative, take this thing, and we can knock that down. It becomes a positive e to the negative x times the quantity 1 over x squared plus 1 over x. Then we take the derivative of the second part and not the first. This is negative e to the negative x times, derivative is going to be negative 2 x to the negative 3 minus x to the negative 2. Once again, I'm going to regret this, aren't I? Okay, so this negative makes those positive. That can factor out. So we got a reinforced, it's 2 over x squared plus 1 over x and 2 over x cubed plus that. Not as awful as I had thought, but still pretty nasty. Yeah, I'm wondering if there's any nice patterns that come out of this. Okay, so that's going to be negative e to the negative x times what we had before. Okay, plus e to the negative x times now the derivatives of those things. So we bring down, he's going to make that a negative 6 over x to the fourth. Come on, man. Minus 4 over x to the negative third, or 4 over x to the third, minus 1 over x squared. Let's make that the negative here. So we get 6 over x to the fourth plus 6 over x to the third plus 3 over x squared plus 1 over x. I mean, we're not going to get like a good approximation with only 4 terms, but why not? So 1 over xe to the x is going to be equal to, of course I erased it, sum I goes from 0 to infinity fi at a over I factorial for here. It's going to be e to the negative first times 1 over 0 factorial, so just that, times x minus 1 to the 0. So we're just going to get e to the negative 1 plus negative e to the negative 1 at x equals 1. Times, this is going to be 1 plus 1 is just going to be 2. Over 1 factorial times x minus 1 parentheses to the first plus e to the negative 1 times 1, 1, 1 makes this 2, 2, 1 is 5 over 2 factorial x minus 1 to the second plus this one is going to be negative e to the negative first. 6, 6, 3 is 15, 16. Over 3 factorial. Second. Okay, so yeah, I mean, I'm just looking at this now, and the Taylor series is going to have the same problem where, right, the radius of convergence is still only 1, so none of this is actually going to work. Oh well. Boo. And it has to be within 1. It can't be equal to. Yeah. Oh well. I'm just wasting time. It's fine. But again, also, you know, somewhat fun, I guess. Yeah, complex function. Yep. I guess that's fair. Yeah, it's been a really long time since I've done complex. Oh well. Again, if anyone is feeling like saving me from myself, feel free. What kinds of things do you want to talk about? So, Tyrannosaurus Rex. Hey, doing all right? How are you? We were just talking about some difficult math and how everything that I was doing was wrong. So, we're having a good night. So, if you have any questions, you'd like to know something, feel free to ask, because we're just pretty much hanging out at this point. All right, so we said the integral of 1 over p times dx is going to diverge when p is less than 1 due to the fact that 1 over x will always be less than or equal to 1 over x to the p when p is a small number, so less than 1. And due to that fact, and we know that integral from 1 to infinity of 1 over x dx diverges, and this. Therefore, the integral from 1 to infinity of 1 over x to the p dx when p is less than 1 diverges. So all of our integrals that we've been working with here are trying to, well, the ones that we've been doing here are mostly dealing with trying to prove that another integral will either converge or diverge. So one of the things that we said earlier was if you've got a function you want to know if it converges or diverges, you can either find a function which is always greater than it, nope, sorry, g, always less than it or equal to on that interval that you're looking at. And if it diverges and it's less than what you're trying to find, then the thing you're trying to find will also diverge. On the other hand, if you go with something that is greater than the function you're looking for and it converges, then it's kind of stopping f here from getting too big. So it will also converge. So then we were looking at this one and saying, okay, what can we do in order to prove that 1 over x to the p dx converge? Well, I think this one, right? Oh, yeah, that's fine. This one you could actually take the integral of it. be integral from 1 to b, limit as b goes to infinity, 1 over x to the p dx, where p is greater than 1. Right, so we get an integral of, it's going to take on the new, it's going to increase in value because it's in the bottom. Right, x to the negative p dx is going to then become x to the negative p plus 1, right, because we're increasing the integral. And then this is going to be 1 over negative p plus 1, because we get the new, yeah, we get the new power in here. Okay. So we're taking the limit as b goes to infinity of 1 over negative p plus 1 times x to the negative p plus 1, where p is greater than 1. Evaluate from 1 to b. Okay, so then right, 1 over negative p plus 1, b to the negative p plus 1, minus 1 over negative p plus 1 times 1 to the negative p plus 1. This just becomes that stuff. This is all 1. That's the limit. So b goes to infinity. B is greater than 1. So 1 minus p, or when it's underneath, right, that's going to be 1 over b. Negatize that, it's going to be p minus 1 when p is greater than 1. Okay. 1 over negative p plus 1 times that. Limit b goes to infinity. Right, as long as p is greater than 1, this is going to eventually tend to 0. Yeah, and I'm just missing a whole term. Jeez. Come on, man. Right. Plus 1 over p minus 1. The whole fraction tends to 0, which means that this whole thing will tend to 1 over p minus 1. P is greater than 1. So it converges. A. Right. So this one you could just do a direct proof. This one you have to do a comparison. All right, well, anyway. Anybody else want to see something else? I was working on something recently. Oh, you know what? One of you all, a couple weeks ago, was it Superbrain? Said it was last week. It was when I was doing Simpson's rule. He said, what about like doing a fifth degree polynomial or something like that? So I did it, and it failed. So that's not going to work. So the major problem was that when you do a fifth degree polynomial, I think I did fifth. Fourth. When you do a fourth degree polynomial here as like your feeder, somewhere down here, it ends up, right, so you get all the terms separated in between my fingers there. You get all the, Jesus. You get all the terms separated, and you're like, okay, now I've got a whole bunch of unknowns that I need to plug in. And when you try to get the unknowns and what they actually are, you end up with a system of equations that ends up having only 3 terms. Yeah, so I said, let's just do a fourth degree polynomial, for example. And so it turns out that like the polynomial that you get is only in terms of the first and last terms. So if it's only in terms of the first and last terms, you've got an x0 and an x sub 0 and x sub 4 in there. Because from the top, we were only evaluating the integral from x sub 0 to x sub 4. So you've only got 2 terms that you're actually doing this over. And then the x sub 4 plus x sub 0 that we get down here is going to, just like our quadratic one, be x sub 2. So now, again, we've only got 3 terms. Man, keep moving it the wrong way. All right, so x sub 0, x sub 2, and x sub 4. So now you've only got 3 terms. So, like, Simpson's rule really does only work on quadratics. But I did have some interesting experience here trying to fit like the coefficients in. So that was interesting. And it popped up with a bunch of like, you know, the Liuhui triangle numbers when we're raising each thing to the 4th power, to the 2nd power, to the 3rd power. I was like, oh man, that's a lot of practice for. So yeah, the higher degree polynomials don't end up working. But it's still an interesting, it was still an interesting exercise in like, how does this work? And then at some point this week I was doing something else and I came across a piece of research and I'm like, I ought to do something with this. And then I completely forgot what it is. So that's cool too. Let's see. What else we got? Woohoo! Meanwhile, our school came out with volume 4 of a journal that we've been working on. It's like student-led papers, things like that. It's really uh, they've been doing really well over the last couple of years. They've been doing experiments on the tobacco hornworm being one of the most prolific species of caterpillar slash moth in this area. Given that we're in tobacco country, essentially. So there's been a whole bunch of research that people have been doing into the tobacco hornworm. The editorial team's like, not another one. Which, no offense to them. The students have been working hard. We've also we've also worn out our welcome in the math division because we, or the previous management who had gotten us involved in creating this thing in the first place, also really pushed toward getting some students doing number theory stuff, and then like practically all the ones that his class had done like involved the Pascal triangle. Again, similarly, they're just like, come on, another project on the Pascal triangle. Come on, can you guys do something else? We also came out with volume 3 while the pandemic was going on. So like we didn't have any physical copies of the thing, but my my colleague who's like the graphic designer and also works in math um, was like, okay, well, we can we can get copies of this thing, but it's basically just going to sit in a filing cabinet for a year or whatever. So we finally were able to get them out and start handing them out to all of our former students who now have moved on, and then we got them to all the students who are on campus. So it was nice, getting to see that group again, who haven't been around in a while. Hmm. I do have online availability, but at the same time, like, or we had online availability, but at the same time, this was like something that these students have really worked hard for, so we wanted to give them like a physical thing to, yeah. I mean, I'm sure you know at least sort of how it is, right? You make a product, you want to have the product. So, oh boy. Let's see here. Yeah. So one of the things that I had been working on was trying to figure out the again how my channel name came around. I was trying to figure out how the n-dimensional simplex can be put into a computer program to find out what all the individual values are going to be. And of course, that's kind of hard. Um, I haven't made any actual progress, but the the main hang-up for me is like learning how to program. And I mean, I've got it in MATLAB, but then I'm trying to do like an n-dimensional matrix essentially, or like a nested list. And my spouse was trying to help me with that earlier on, uh, with mixed success. It's not easy, particularly. But I've contacted the um, person in engineering who is going to print, like 3D print a physical object. So, like, it's, I can find any one number I want, right? But my project that I was working on was to not just find any one number, but to take like the entire slice of that particular simplex and then find the sum of that row. So on the Pascal triangle, that one's easy, right? You're doing like 1 1 1 1 2 1 1 3 3 1 1 4 6 4 1. And then to find the sum of all this stuff, it's just going to be 10, 15, 16. This one's 8. This one's 4. Oh, by the way, it's square numbers. So that was interesting. And then I was like, okay, what's my dean was like, okay, there's probably something interesting here. Which for this one, yeah, okay, the ratio is just going to be 2. Not super interesting, but it's there. And then I had said, okay, if you on each row instead sum up like n rows above it, what do you get for that? And then what are those ratios? So I'm kind of spilling the beans here. So this is 1. This is going to be 3. This is going to be 4 plus 3 is 7. Which also I think this ends up being... I can't remember if... No, this isn't Fibonacci. This is... There's something else. But like 1, 3, 7. This one's going to be 8 plus 6, 14, 15. Oh, it's just... Right. Yeah. 2 to the m. Realized it pretty much at the same time there. Yep. Which then again, if you're doing the... if you're trying to find the ratios between them, that's 31/15. And then you're eventually getting something that is just off of 2. So obviously it's not 2, it's slightly more. I think that when we get down to some ridiculous number of rows down here, this actually becomes, yeah, this should be, ratio is going to approach 1 plus root 3. There was something with it. No, I know what you mean, though, because it's only off by 1 for each of these, so it should be. Maybe I'm doing this wrong. uh, no, I plugged this into a spreadsheet. Damn, where's the spreadsheet? It's got to be here somewhere. Oh yeah, drive. Here we go. Share, no, my. I mean, it has to, right? Oops. You're seriously. Come on, man. Sign in. All right, whatever. Unless it's only on my computer. Could also be only on my computer at school, in which case I'm not getting it here. I can tell you that much. No. Whatever. Okay, fine. Yeah, that's too bad. Wait, hang on. Did I bring it home and put it into a different drive? That's not what I wanted. Documents. Research. Nope. Okay. So, easy way, I guess. 1023 over 511 should probably be pretty close to 2, right? Yes. Yep. Yeah, they just don't call it a tetrahedron because that implies four-sided, so they're like, So um, I have a friend here whose father is like pretty involved in math research, or at least used to be. He's professor emeritus at this point. And yeah, I started using the, weird incorrect terminology. I mean, not that it's completely incorrect, but just that I was like, yeah, you're doing this n-dimensional tetrahedron, and he's like, it's a simplex. Like, oh, okay. Just gotta curl back into my hole now. Yeah, now it's converting to 2. There's something else. I'm missing something. I don't remember what it is now. But I'd have to find it in my Oh, the idiot. That's what it is. It's not that. Okay. Hey, I figured it out now. All right. So it's not this. It's not this. It's that when you start looking at the triangle itself, the individual terms inside the triangle. There we go. So we go down like this. This is still going to be 1. This is now going to be 2 here. This is now going to be 3 here. And this is going to be 2 here. If we sum up everything above any particular number, so this one is going to be 4 from those. This one here is going to be 5, 6, 7, 8. This one's also going to be 8 by symmetry, and this one's going to be 4. 8's on the outside here. Inside is going to be 12, plus 5 is 17, plus 3 is 20. So 20 and 20. This one is going to be 16, 18, 20, 23, 24, 25, 26. This one, that's the one. So if we sum up everything across the row here, it's going to be 1, 2, 2, 4, 7. This is 16, 24. And this one's 40, 66. And 16 is 82. Right? So then, is that the one? 82 over 24 is 3.416 repeated. I think I'm wrong with this one too. Hang on. 3.416 repeated. Yeah, no, because that's too small. The hell was I thinking? There's something here. Anyway, whatever. So, yeah, when you sum up all these things as you keep going down, and every individual term is the sum of everything above it, and then you try to find the sum going across the rows. And unless I screwed this up somewhere else, always possible, then the ratio of one of these things had something to do with like 1 plus the square root of 3. This one was like 2 plus the square root of 3. Or 2 plus the square root of 3. Might be. 1 plus 2 square roots of 3. Yeah, I think it might be that one, but yeah. So, it's something to do with one of these. Anyway, it's been so long since I did this research is really the problem. My jaw just about hit the floor when I saw this, because I was like, wait a minute, I know that number. Like I started pulling digits and trying to make like a recursive fraction out of it to try and figure out what the actual values were for it. And like that didn't yield a pattern, so I was like, okay, that's weird. A lot of the recursive fractions have a pattern in the number that's loose. So it's like, 1 plus 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 5 plus. You get like Fibonacci sequence and all the numbers out front or something like that. Yeah. God, I always hated that in textbooks and stuff, but it was actually somewhat useful. That was weird. But yeah, anyway, so a lot of these recursive fractions, if you come up with like, 1, 1, 1, 2, 3, 5, 8, 13, etc., and get Fibonacci sequence in these places, it comes out to some interesting value. And it's some sort of fraction or some sort of decimal that is an interesting number. But the one that I found for whatever this was just like, yeah, no, that's not even remotely close. And yeah, it came out to one of these things, and I recognized root 3 because I've been teaching trig for 10 years or whatever. So I see something that involves the square root of 3. I'm like, that's something. So I was able to pick it out finally. Anyway. Yeah, it was a fun little interlude that I was playing around with this thing with my former boss. Or really, I'd done the work, he'd given me some ideas. It's typically the way his stuff goes, is that he kind of gives people odd prods here and there, and I'll just I'll end up doing, the work for it. But he's an advisor. That's how he does it. um, all right. I think we're coming toward the end of this one. But if anyone has any last minute questions, feel free to ask. Oh, yeah, this other one that I did. One of my students was working on like, uh, can we get a I wasn't wearing the proper shirt today, but can we get a magic square of squares? So can we get, a squared, b squared, c squared, d squared, e squared, f squared, g squared, h squared, I squared. Not imaginary I, but the other one. And so she was working on this particular question. Yeah, she was working on this particular question, and I ended up being her advisor for a little bit. Not really seriously, because I'm not a good advisor. Oh, did you see that somebody cracked it recently? I mean, not fully, but somebody had made a some sort of progress on it. I was quite impressed. Yeah, somebody made some sort of progress. I don't remember what it was, but Matt Parker did a thing on it uh, on Numberphile. So he he mentioned the return of the Parker square because like they had actually termed um, they had actually termed the Parker squares the ones that like had an off diagonal that didn't work inside of the rest of the thing. So they termed it a like, we have a non-Parker square, and he's just like, oh, man, the name did stick. I mean, he was expecting that, but I'd worked out like she'd done a bunch of she realized that you could actually set this up, and I'm sure you came up with something similar. So if you look at these two, like the row and the column, right? Then you're gonna get an a squared term that's in both b squared and c squared. Or sorry, that's wow, in both the row and the column. And this generalizes to every row and every column, right? So there's always one thing that's intersecting. So then we need a squared plus d squared. I'm going to move this plus g squared. I feel pretty confident in sharing this because she's off doing her own thing now. Last I knew, she was working on quantum computing. Right? And if we swap one of these around so that we end up with, let's do, it doesn't matter, minus b squared minus g squared minus b squared minus g squared. So this is going to end up being c squared minus g squared must be equal to d squared minus b squared. And again, without loss of generality, pick any one you want. Any row, any column, there's always one thing that's going to drop out, and then you can rearrange stuff so that you have a difference of squares. So then the difference of squares is going to get you c minus g, c plus g, and d minus b, d plus b. Interesting. So what she did was she said, okay, these have to have these have to be factors of the same number, right? So all of these are integers, first of all, and we're assuming that we always pick, the larger one is being subtracted by the smaller one. So these are the difference of squares on both of these are going to be positive. So just, again, generalize, that's how we're going to do it. And again, they're going to be equal. So these are now factors of the same number. So c minus g, c plus g are going to be factors, and d minus b and d plus b are also going to be factors. So then, now I can't remember what order she did this in. You know what? I have pictures. Some of her preliminary stuff she sent me on, like text. Okay, she didn't go that far. I see. So she said, I'll just leave it. She said if we take this one to still be c squared minus g squared, then again, without loss of generality, choose your pair. I think she did. Okay. She said either. So we know that d minus b is going to be a factor of c squared minus g squared. So therefore, that must divide c squared minus g squared. And also, d plus b must also divide c squared minus g squared. And then she went through an interesting little thing, which was if you have c squared minus g squared, right, this difference of squares has to have either 0 or 1 mod 4. So she was able to come up with like charts of just stuff that was like, okay, if C is going to be, 0, 1, 2, or 3 mod 4, then C squared is going to end up being also 0, or if this is 1 mod 4, then squaring it is going to leave you with, I think it's still going to leave you mod 1, hang on, or 1 mod 4. So if it is 1 mod 4 squared, means we're going to take something that is 4n plus 1 and square it. Yeah, right. Because this is going to be 16n squared plus 8n plus 1. And then this stuff is going to be 4 parentheses 4n plus 2. 4n squared plus 2n plus 1. So we still end up with 1 mod 4. All right, and then 2 mod 4 squared is, again, going to be 4n plus 2 squared, which is 16n squared, plus 8, 16n plus 4. And with this being a 4, now you're going to divide a 4 out, and everything is now 4n squared plus 4n plus 1 inside. So that's all, yeah. So we end up with here, this is going to become 0. And similarly for 3, you can prove that this is going to be 1 mod 4 when you square it. So 4, nope. N plus 3, when you square, ends up 16n squared plus 1224n plus 9. So here you can split out 8 plus 1. The 8 becomes part of that, and then you get a plus 1 at the end. So she said that c squared has to be either 0 or 1 mod 4. G squared, similarly, has to be 0 or 1 mod 4. So then the only possibilities that you can get for that are going to be right, C is this, G is also 0 or 1 mod 4. So then she said, if we work on this, it turns out that if... I'm going to botch this. Okay. It turns out that if we let... God. Yeah, okay. So if c, oh wait, that's c squared, sorry. C squared, g squared. Apologies. So she said if, yes, hello Woodcraft. Yeah, this is a crappy old bamboo tablet from 10 years ago at least. It is an MTE 450. So I have to say, this particular product is actually pretty good, but the driver is no longer supported. So that means that I, on my computer, can install the driver just fine because I have administrative access and all that good stuff. When I go to my computer at school, I plug it in and it works as a writing tablet, but I can't customize it. I can't change any settings whatsoever. I cannot change I can't change anything. So I'm actually looking at potentially getting a I think Intuos, which is has a larger writing area and a bunch of other cool stuff like that. But that's that's a little ways off. So we'll wait until if affiliate happens, and we'll start investing some cash into that, but we'll wait. Of course, I also need a new graphics driver, but that's neither here nor there. Or sorry, new graphics card, but yeah, that's not going to happen for another year, I'm sure. Anyway, so welcome. If you have any questions, let me know. Superbrain and I are mostly just kicking around an interesting research problem that one of my students was working on a few years back, and she hasn't done any work on it, so I figured I'll just let it out to the public and show her particular approach, and if anybody wants to pick it up, feel free. But... Yeah, you got auto-modded there. So no, so I work at a two-year school, two-year college, and so my student was working with us for a couple of years. She also did a research project at a local university. Um, while she was working with us, she also went there for like a couple of classes and worked with one of their professors on quantum computing. And allegedly, allegedly, they had basically emulated a quantum computer using a standard computer, and I was like, hang on, that's not possible. Like, I mean, like really emulate, not just like, oh, it's a fake thing that sort of works. No, no, like they fed it stuff and it would spit out the actual quantum computer answer, and I'm like, that can't be right. And so we had discussed it at some point, and they were like, yeah. So anyway, it was an interesting idea. I don't know what ever came of it, if anything. Um, well, allegedly it worked in polynomial time, but again, that was like, but that's it's not physically. Yeah, the old red versus blue. That's not physically possible. Um, but at any rate, hmm, interesting. Anyway, woodcraft. Okay, interesting. I have not seen that one. 8,200 levels of pressure. Hmm. Yeah, being $60, that looks kind of interesting. XP pen. Deco. Well, Creative Block seems to like it. Gets about 3.5 stars. Or the this was the Artist Pro, so technically not the same thing. The Deco gets 4.5. Yeah, that's interesting. Comes with an XP Pen drawing glove. Yeah, I have an Arctica glove somewhere. It must be in my office. I've left it behind somewhere. So it means that there's 8,200 like possible data points for the amount of pressure you put on it. Yeah, yeah. So on this one in particular, like if I just draw very lightly, you can see that this is kind of like a pen where you can draw just a little, but then if I press harder, I'm gonna break my pen. Aw. Yeah, I just made the. Aw, that's not good. I might have just broken the tip. That's fine. But yeah, you can tell, like, depending on how hard you press, it does differing. Yeah, you get what I'm saying. I mean, this thing is also 10 to 15 years old, so it's probably about time. Oh, there it is. I see. Okay. It actually, like, the sleeve part popped down. So there was a little space here. So it just kind of snapped it together. It's fine. So I just have to be careful. Okay, so what this student did was she said, if I go with this and say that what was it? If we do like basically a Punnett square, where you get like C and G are going to be are squared. Nah, we'll do C and G. So 0, 1, 2, 3, 0, 1, 2, 3. Then G squared and C squared are going to end up having, or C squared minus, sorry. It's been too long since I've done this, so it's not fresh in my brain. C squared minus G squared is going to have this mod value. So this is going to be like 0 minus 0 is just going to be 0. Right? C is going to be 1 minus 0 is going to be 1. 2 minus 0. Oh, wait. But that's C squared. So that's also going to be 0 minus 0. It's going to be 0. 3 is going to be 3 squared gets us the 1 mod 4 minus 0. So that's going to be 1. This is 0 minus 1 is going to be negative 1, which mod 4 is 3. Or we could leave it as negative 1 if you really feel like it. This is 1 minus 1, so we get 0. 2 gets us a 0. Minus 1 is going to be a 3 again. And 3 minus 1 is 1 minus 1 is 0 again. 0 minus 2, 2 is 0, so this gets us a 0. Right, 1 minus 3 is going to be 1 minus 1, so that's also a 0. 2 minus 2 is a 0. 3 minus 3 is 1 minus 1, it's a 0. And then 3 minus 2 is a 1 minus 0 is a 1. 1 minus 2 is a 1 minus 0 is a 1. 0 minus 3 is 0 minus 1 is a negative 1 is a 3. So I should get rid of this part right here. So really what we've got is C squared minus G squared mod 4. It's tiny, it's fine. All right, then this is 2 minus 3 is 0 minus 1 is negative 1 is 3. So then she also looked at when C squared minus G squared was mod 2. Like, what is this going to do for us? So it splits up, again, based on whether you have mod 0 or 1 mod, sorry, 0 or 1 mod 4. if you also do this in terms of mod 2, some of these options just kind of delete themselves, and it's not physically possible to have some of the combinations. So then she looked at this and said, okay, we eliminate some of the combinations. So that means that like B and D then have to have certain modulus mod 4 in order to make all this stuff work also. And again, those are B and D have to be also factors of c squared minus g squared, just as much as c minus g and c plus g are. Maybe I'll come back and do this some other time. once I've actually read it. This doesn't seem physically possible. Alright. Anyway. I think it's getting to be about that time. So, we're gonna... Unless anyone has any questions that they want answered. I'm going to find somebody. Right, we can always do Jason Charles Miller. He's pretty awesome. If we do category, I assume nobody but me is live. Yep, okay. Science and tech. Alright, got a bunch of people who are doing software development, but nobody is really doing math, so. The one with the Surface Pen? Sorry. Sum of signs of rational values needing to be 0. Somebody's making a duck hunt AI. That's interesting. Magic square of squares, yeah. Okay. That's interesting. Sum of signs of rational values. What the hell? How'd that happen? Oh, were you doing stuff on like a grid and so it was sweeping around? I think I've seen that before or something. Not... Yeah. Not in that context, but I've seen that happen with like the... I tried doing that with the Ulam spiral. So when you're trying to get all the prime values going out in a spiral, or sorry, all integers going out in a spiral, and you highlight all the prime integers. I tried doing something with like a similar, you know, I'm going to sweep out and try to find all the primes. And yeah, that didn't work. I see. Yeah, something like that happened to me with one of my projects too. It was the n-simplex. Finding the individual values of any n-simplex I mean, I call them n-simplex pachinko because that's that's where my channel name came from. Yeah, so if you create the, you know, Pascal or Le Hui simplex in n dimensions, whatever dimension it is, then the individual. I gotta remember what this is. Yeah, and I mean, literally, I'm in the three-dimensional model. It's playing pachinko, right? You drop marbles or whatever into the top section, and just like my the nope, down there, the channel that way. There we go. The channel logo, right? If you look at the larger version of it, which should also be on my banner, but I have to talk with my artist. Because the one that's there is me doing it, and I'm terrible. But yeah, I've talked with one of my friends who's an artist. He's gonna make some stuff for me. Yeah, I'm gonna have him make some stuff for me on commission. Um, and yes, my artist. He's just a friend of mine, but you know, he's like the guy that I go to if I ever want anything interesting. And I mean, this would be the first time that I actually do something for stream, so like that's really cool. I've had him do a few other art pieces, but it's always been like, you know, in completely different contexts. Uh, anyway. Yeah, what was the... Hang on. Yeah, okay. So if we do... Here we go. K subsets with K dimensional spaces, all this stuff. This is good times. So if we look at higher dimensional combination, permutation, yeah. If we go to higher dimensional permutations, this ends up being, come on, where is it? Yeah, there we go. So the notation that this person uses, who is this? I better cite my sources. Igor Pak. Oops. When and how n choose k. So he went down and he said that if we do this on n choose k in q dimensions, then we do this as n factorial divided by k factorial q n minus k factorial q. Now there's a nicer way to do that with, like, you know, pi. You're doing a pi operator, having it multiply, but I'm not finding it immediately, so I have to look for, I have to find my notebook. That's a pain. So it's like doing that in Q dimensions, which again, I'm trying to find the notation that I used for it, which would make this a lot easier. Oh my god, there's an upside down pi notation. Oh. I didn't know that was a thing. I know. I'm trying to find it. Boo. How dare he not use the exact notation that I want. Um, Alright, so Wikipedia, n choose k. Here we go. Hang on. This might be it. Alright, so the notation that I used was... Okay. So this was a plus b plus c plus dot dot dot. Whatever this is going to... Nah, it's terrible. A1 plus a2 plus a3 plus dot 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 out to a sub k, right? So you have k things that you're choosing from. And this is raised to the nth power. I think this is how I did it. So as you go down the rows, this tells you how many choices you have in k dimensions. I think so. So then you're saying that you want n factorial. Really hope this is right. Over k1 factorial, k2 factorial, all the way out to k sub n factorial. This is, hang on, I'm not doing it right. Okay, so with the three-dimensional, let's look at the three-dimensional one, right? So if I want 1, 1, 1, 1, 2, 1, 1, 3, 3, 1 along the faces, 1, 4, 6, 4, 1. If I want out along the face, this is going to get me like n going this way. Okay, and then I have to choose the other two dimensions. So so I'm going to have to choose a direction this way and also a direction this way, back into the simplex. So it also includes the stuff inside the simplex, which the faces are all the same as the Pascal triangle. But the stuff in between them is the interesting thing. Yeah, okay. So n is coming down, and then k is choosing like over and back. How far over and how far back into it are we going? So, yeah, well, it's possible. I'm also not well versed in projective planes, so that's probably also why this is going. me find my notebook. Be right back. Alright, that might not be actually the right one, but whatever, it's fine. No, that's my... Yeah. That's differential equations. This one's too new. I have one notebook that's like absolutely falling apart. I think it's that one. Okay, so I duplicated my work here, but I don't actually have the thing. So that's slightly annoying. Yeah, now that is the interesting thing. Okay. So I can attempt to draw this. It's a little hard because, you know, it's in 3 dimensions, and this is not. So basically, the way that I formulated this was you do, you know, 1 for the top. You end up with 1, 1, 1 for the second layer. So you get a nice little triangle around each of these, and then this is projected downward. This technically is only a point and not that. And then along the side here you get 1, 2, 1, 2, 1, 2. Along the side you get 1, 3, 3, 1, 3, 3, 1, 3, 3. And then the middle here is the sum of the 3 balls above it. Or I do this in terms of sphere packing. So if you think about them as individual spheres that are stacked up in a tetrahedral fashion, this becomes a little bit easier. So these three, the 3 2s that are up here, are the ones that are touching the 1 in the center of this one, so this is a 6. Alright, and then if we make this bigger, this is going to be 1, 4, 6, 4, 1, 4, 6, 4, 1, 4, 6, 4, 1. In the center here are going to be that's not helpful. I think it's 3. Yeah, they're all stacked on top of each other. So I think there's only 3 in the center here. And all of them should be... So they're each touching 3 above. So, like, this one here is going to be touching these 3. The 3, 3, and the 6. Yeah, 12. And then this one up here is going to be touching this 3, 3, and 6. And then this one here is going to be touching this 3, 3, and 6. Yeah. So it then keeps going, and yeah. It's going to be all sorts of messed up. So I tried doing like subscripts and all sorts of fun stuff like that. Tried like solving for all sorts of stuff. Oh yeah, I tried doing this in 4 dimensions. So eventually, like, there we go. Saying like, okay, each one of these things, given the 4 subscripts in this sort of picture over here, is going to be like, yeah, it's it gets to be like the 3-dimensional tetrahedron is like the shadow that's going to feed into the, yeah, it's going to feed into the 4th dimension. So it's, yeah, or what it is the 3-dimensional tetrahedron is the face, in the same way that the 2-dimensional Pascal triangle is the face of the 3-dimensional tetrahedron. The 3-dimensional tetrahedron is the face of the 4-dimensional simplex. So yeah, it gets really messy really quickly, and I've got like all these nested subscripts and stuff like that. So I was like, okay, what is it that you're adding up from the previous thing to get the new thing? And when I finally did that, I got pretty proud of myself, but it was just hard. No, I just took that out. I just put it away. This is not the one. Bah. Oh well. Yeah, so like in 3D, I ended up like shadowing in all of the other ones that produced. You can't really, nah. So like all the ones that produce the ones that are here, I like made them as small light circles on the inside of the other triangles, and yeah, it just got really messy. I gotta contact the guy who's trying to make the actual simplex there, three simplex, in order to see what he's gonna be capable of. I think, in theory, we should have it like I think he was done with it before the pandemic or like December of the pandemic, but I just haven't contacted him. I don't know. It's basically a $200 toy. But I'm also not paying for it, so but yeah, I was like, okay, let's create this thing. It's gonna be like nested hexagon, or it's gonna be hexagons. So like my starting soon, ending soon screen here, right? This thing, bottom left corner, allows the ball bearing to hit like the center point of those three hexagonal prisms. It'll then fall in one of those holes, A, B, or C, and then depending on which one it goes into, it's going to fall down through and go to the next layer. And then on that one, you see that there are two possibilities to land in each of the middle hexagonal prisms, and only one possibility, one path to land in the far extreme three. So when that when that goes that way, we end up with these really cool patterns. And again, that's this one here, that one there. So 1 2 1 2 1 2. It's basically I was only able to put in together in one picture this layer and this layer. So that is my terrible artistry, which I had freehanded that before, so it was really bad. And then one day when I was home from school, I was like, all right, let's just knock this thing out. And I did like a bunch of straight lines, and actually, yeah, a bunch of straight lines, actually using the ruler. Imagine that. I did some actual like copy paste and Photoshop work. It was weird. Who'da thunk? I mean, technically, right? The infinite simplex has to have all the knowledge, but therein lies the problem. Is so I am constructing each of these from the previous layer or the previous dimension. So all of them are built in this way from implicit sequences. But you can actually find it using an explicit sequence. So that was what I was talking about earlier, is that if you try to build this in n dimensions directly, you can do it. It's just that I don't have the algorithm right here. All right, let p be an integer such that p is greater than 2, and all of our individual terms, k1, k2, k3, etc., to k sub p are natural numbers, and n has to be equal to the sum of all of those things. Okay. p of k sub I. And must be greater than or equal to 1. Yeah, okay. I got it now. All right. So when you pick oh, damn. Whee. So this is basically saying that we're doing n choose from K1, K2, K3, K4, all the way through K sub P, not N. So if we go up here, we can change this one to P up there. Yeah, so in the three-dimensional one, we're choosing N going this way, and then we're going to choose K1 going this way, and K2 going this way. So if I want like this one right here, if I wanted to know what this was, this would be n equals 0, 1, 2, 3, 4. So 4 factorial, God, I hope this is right, over k is going to be, is it 0? Yeah, right. K1 choose 0, 1, 2. K2 choose 0, 1. It's 24 over 2. Yeah. Okay, cool. It's 12. All right, cool. So that's how that works. And the thing is that K1 and K2 can be any of the dimensions as long as you're creating them as, you know, essentially perpendicular. They're not literally perpendicular, but they're orthogonal in this particular setup. So your K1 is going to be the horizontal distance, counting starting with 0, and then K2 is going to be the diagonals. So if I want like the, again, if I went 1, 5, 10, 10, 5, 1, if I want K1 going this way, K2 going this way, 5, 10, 10, 5, 1, 5, 10, 10, 5, 1. This is going to yield 1, 2, 3. So 6 new numbers on the lower level. And then these are going to have a pattern that is just similar to the stuff up top. We're going to get the sum of these three. So 4, 4, and 12 is 20 on the corners. And the ones in the middle are 12, 12, and 6, so 30. Now if we want to prove that, we could say that this is n equals 5 over here, K1 is going to be 0, 1, 2, and K2 is going to be 0, 1 to get 20. Right, so then this is going to be 120. Nope. Ah, shit. Hang on. Something not right here. Do I need the remaining? All right, let's diagnose. 120 over 2 is going to be 60. 2, 1, 3. What's remaining? Yep. So this is going to be n minus parentheses k1 plus k2. Okay. Oh, man. Factorial. No, that's not right either. Jeez. Well, yes. I mean, true. Geometrically orthogonal is just the same. No, I just need this number to be divided by 6. So that's 3 factorial. Oh, you know what? 0, 1, 2. 0, 1. Which should be symmetric to this one. 0, 1, 2, 3, 4 by 1. Man, I really screwed this up. Alright, so how are we getting this? Yeah, it should be. Sure should be. Zero, 1, 0. Oh, yeah, it's the other diagonal. All right, cool. Thank you. Oh, yeah, because you've got to pick an origin point and be consistent about that origin point. That way. This is our origin point. Jeez. Thank you. All right, so that's not right. That's 0, 1, 0, 1. So yeah, 1, 1, and 3 factorial is the leftover bit. Thank you. So this is the remainder. N minus parentheses k1 plus k2. Really, it's the sum of all previous k's, right? So then that's going to still get that. That is our k sub p, technically. All right, so then the 30 is going to be 0, 1, 2 by 1. So we get a 2, 1, and another 2. So that's going to divide by 4, and we get 30. Yep. Okay, now that we've got that, right, if you want the 12th row, then 6th in and 5th up. This is going to be 12 factorial over 6 factorial, 5 factorial, 1 factorial. So that eliminates everything 6 down. So 12, 11, 10, 9, 8, 7 over 5 factorial is going to be 5, 4, 3, 2. So 77 u times 12 times 6, 72 by 77. And just because I feel like being a masochist today, 2 is going to be, right, we get the 1s by doing 14. 7 times 2. We get the 10s by doing 7 times 2 and 70 times 2, and also 7 times 70. So this is 49 plus 14 plus 1. So 50 plus 15, nope, sorry. 50 plus 14 is going to be 64. And we get the hundreds by doing 10 times 10 is 49 plus 6 is going to be 55. So 5544 is going to be that particular 12th row down, 6 in, 5 up diagonally. And the symmetry then works. So all of our combinations of 6, 5, 1 in any order are going to all be 5,544. So this works in general. And now if you want the... Here's your problem, Superbrain. If you wanted the infinite factorial, right, then now you've got a problem. Because now you've got to choose an infinite number of terms that you're going to multiply together, which are all factorials, which are going to eliminate some of the infinite factorial. But it can only be a finite number of them. I guess it eliminates an infinite number of them, but they're... Anyway. You're going to have some problems. That's what I'm trying to say. All right. For real, though. All right. Let's actually go see Jason before he closes up shop. Because I think they're maybe getting close, but... Let's read the channel for Jason Charles Miller. Oh, so hey, Hurdler and Diablo, thank you for the follow. I didn't get to you, well, you followed before the stream started, so you know. At any rate, thank you everybody for coming. This has been Obi-Wan Pez for N-Simplex Pachinko. We're going to be talking more about math next Wednesday, so feel free to come on by. And on Friday, we're going to be streaming some more spooky type stuff with Outer Wilds. So I've got some new ideas about things to find. I was sitting in on somebody else's stream who was doing like early stuff, and I like some more ideas. Both were slightly spoiled, but whatever, it's cool. Or like I knew that was a possibility. Or we found some things to discover, and we talked a little bit about some interesting things that were out there. So anyway, see you on Friday, those of you who are interested in Outer Wilds. If you've never heard of it, and you have Game Pass, look it up. It is a fascinating game, and I love it. So, Outer Wilds. At any rate, hope everybody has a good night. Happy Wednesday-ish. And hopefully we'll see you next time. Jason Charles Miller is a sort of rock cowboy who has been doing stuff for Geek and Sundry, Q Times, and a bunch of other independent people, and Critical Role, so if you know any of them. At any rate, have a good one. See you later.